This is our final project on the comparison of self-driving planning and control algorithms by Trautman and Siddant Yadav. The controllers that we have implemented are the Stanley controller, the basic longitudinal controller, and the PI longitudinal controller. The planners that we have implemented are a basic planner which follows the middle of the lane, and then an A-star planner. The way this all integrates into our system is the planner takes in boundaries, location, car location, and obstacles, and then generates waypoints and target speeds as needed. And then the controllers use these target speeds and waypoints to control the steering angle, throttle, and brake, which affects the vehicle dynamics, which again updates the simulator ground truth.
So for our two controllers, in the final version, we ended up using a Stanley controller for the lateral control and a PI controller for the longitudinal control. The Stanley controller calculates steering angle from the heading air as well as the cross-track air, and it allows us to use a high speed and keep very steady control due to the ability to get back to the path without swerving. For the longitudinal controller, we used a PI controller, which calculates 5 radii of the path ahead and then breaks it up and uses the radius of the segments to determine the target speed. And the closer to the corner and tighter the turn, the lower that target speed will be. And then we also use distance from obstacles ahead to also set a target speed. So it will pick the very minimum of all the different target speeds we've calculated. And then from there, we feed that speed into a PI controller, which adjusts the throttle and brake to meet the target speed quickly. And this improved our score by a pretty significant margin because it will allow us to speed up and slow down much, much quicker. And it also helps us avoid obstacles because we can brake as hard as possible.
So for planning, we used an A-star algorithm mainly. In our final checkpoint, as you saw, our car was swerving around the obstacles, which wasn't the best option. So the way we stabilize this algorithm is by splitting the track into 3 lanes and then setting the goal for the car to be an empty lane. So our A-star chose a goal in a lane that was empty instead of choosing to set the goal in the middle of the lane and just swerving around the obstacle. When we were implementing our A-star, we noticed that it sometimes generated unstable paths that caused our car to zigzag. So we only used our A-star waypoints when we needed to, and this needed to would be when we detected that there were obstacles in a 50-meter radius. We also improved the motion model of the A-star algorithm by adding slightly less steep paths because the motion model that we were previously using only went in straight or 45 degrees. We added more options that included 30 degrees, 35 degrees, and 60-degree paths.
So here are our results for 3 different scenarios. The first is the simple planner. And this is when we were not testing with obstacles at all, so we could run the car at a higher speed. And then the second two are with our A-star algorithm, just one without obstacles and one with. And as you can see, those scores are on most tracks pretty similar because we're able to pretty effectively navigate the obstacles. It's just we have to run at a slower top speed. We also were able to have no collisions on any tracks, so that was a very good success. And then here you can see our comparison versus the baseline. So we're pretty happy with these results. We were able to pass the baseline with our simple planner by a pretty big margin, and then also pass it, albeit by much less, with our A-star algorithm. And then when you add obstacles in, we are able to pass the baseline by quite a bit with our A-star algorithm. And then we have the same amount of collisions.
This is going to be a demo of our vehicle on the T4 track with obstacles. Here you can see the car is just driving in the middle lane because there's no obstacles it needs to avoid right now because all the obstacles so far have either been in the left lane or the right lane. Coming up here is the 2 cars on the middle and right lane, so the car is going to choose to go to the left lane in order to avoid these obstacles. And now that there's a car in the middle lane, it's going to choose to stay in the left lane and then stay there until these 2 cars come, in which it will decide to go to the middle lane.